So welcome everyone to the last class of this assignment solving sessions. So because this course is actually for this is an 8 week course, and this is the last installment of the week 8 class, right? So in this week, mainly atomic force has been introduced and discussed. Atomic force microscopy. So this is also a class of scanning probe microscopy, and we know great we know an extensive about that scanning tunneling microscopy, which is also part of this scanning probe microscopy. In the previous weeks we already learned that, and this is the one more thing, one more class of this family, right? That is atomic force microscope. And from the name you can see that there's a force. So that means depending upon the measurement of force, actually we are depicting, we are getting the image, or we are getting the microscopic image kind of thing, right? Now, in case of scanning tunneling microscope, that time there is something called tunneling current, right? So that time we are measuring the tunneling current and the between the tip and the surface or the sample, right? So that times your tip as well as the surface must be conducting, right? So conducting surface and tips required in case of steam, because we are measuring the current, and that's why this technique is limited towards the conducting surface, like conducting surface or some kind of metallic deposition can be measured. But the whenever we are measuring the force, because any kind of molecule are actually having some kind of intermolecular forces, like so the force can be of three types mainly. So one can be if the molecule has some permanent dipole and it can interact with another dipole. So it can be dipole dipole interaction. Then one dipole can induce dipole into the other molecular other atom. That time there will be dipole, induced dipole, or if let's say this let's say the tip and the sample or the surface are both uh, they don't have any permanent dipole moment. Still, they can attract towards, like they can interact with each other by the force of induced dipole, induced dipole. Mainly, this force has been termed as London dispersion, right? And you can find this thing, and also Sir discuss this thing in a detail in the first lecture of this week. Like that is the, I feel, 37, right? So 37, lecture number 37. You can find it, that London dispersion force. So what is this? Nothing basically. So any atom is having kind of a nucleus and electrons are revolving around it. So at an instant, like in a momentarily, it can create some kind of a momentary dipole moment, right? So it's still there. Let's say their electron cloud is actually make a kind of gathering towards there. So that time it will become delta negative. So then this induced dipole, momentarily induced dipole, can again induce dipole into the into the neighboring molecule, so delta plus, and then it can interact. And this induced dipole interaction is ubiquitous. Like it can be found in everywhere. So this force is actually present everywhere. Every two atom, every two molecule are actually going to interact in this mainly three, like this maybe these, or if it doesn't have these two, then it will obviously going to have this kind of induced dipole interaction. So that's why atomic force microscopy can be used for any sample. We use this microscopy to get molecular information, to atomic level information of any molecule, and that's why it is broadening uh, like the applicability. So these week questions are mainly from this atomic force microscopy. Like there is no single questions that are not from atomic force microscopy. So actually, Sarah has actually given the basics of atomic force microscopy, how it is actually working and all. So in this today's discussion, at first I also want to give you some kind of a basic introduction so that you can remember the things again. Then we will answer all the questions, all the 10 questions, right? And also I want to tell you that today from 7 to 7 p.m. to 8 p.m. there will be a revision class where I will not discuss anything as such, but I will be talking about what are the things that are discussed throughout the course in for this 8-week course, and what are the things you need to read before going to the exam. It's not like suggestion. It's like kind of recapitulating things. Okay, and that will be there in the 7 to 8 p.m. class. That will be a revision class, right? So before solving this assignment 8, we will try to give a brief introduction about what is atomic force microscopy. So this is the schematic diagram of atomic force, right? So there is a sharp tip. In case of STM also there is a sharp tip. This is a sharp tip, right? And this hard tip is not like alone. It is actually embedded in a cantilever. This is the cantilever, right? This is the cantilever. And this cantilever is actually stuck into the a piezoelectric scanner, right? So what is piezoelectric scanner? Piezoelectric material are those material which can change its dimension in presence of voltage, like different voltage, different electrical voltage can change its dimension to a different thing. Like if you apply some kind of voltage, the material is going to change its dimension to some extent, and that is called piezoelectric material. So this cantilever is actually connecting towards a piezoelectric material that is called piezoelectric scanner, so that like that this dimension change actually help this cantilever like reflect to according to the forces it is going to sense, right? Now here, like just the above cantilever, there is a reflecting surface, reflecting plate or reflecting surface, you can say, where some laser light is coming and reflecting, right? So this is a laser source. There is some kind of source is there, which is actually providing the laser. So this is coming like this and reflecting in the cantilever and going towards the detector. So this is a photo detector. This is called as position position sensitive photo detector. I'll talk details about this, how this photo detector works, how this tip, how it should be, what should be the material kind, so that we can get good pictures and all. I'll discuss all this. So this is a basic schematic diagram. So the light is actually coming and reflecting from reflecting from the cantilever surface, above part of the cantilever, like the opposite part where the tip is actually, this part is tip attached, so just the opposite part, the light is actually reflecting and going to the photo detector, and it is like pointing to it is actually reflecting to a some certain point. Now, depending upon the surface topography, this cantilever is going to like response, because depending upon the topography, the distance between the surface and the tip is going to change, and that is in turn change the force between these two, and then obviously the tip is going to like move upwards or downwards depending upon the uh, kind of interaction it is going to have, and then the position is going to change. And this change, because this detector is nothing but position sensitive. So what does that mean? That means at every like other position it is going to give us a different kind of voltage. Detector is basically photo detector is measuring the photo voltage. So at different positions the voltage are different, right? Just let me check this 1 second. So this is the case. So depending upon the topography, the position of the reflection is going to change, and so that we can get the idea about the topography. I'll discuss this in detail. So this is the PSD, or position sensitive photo, PSPD you can say, or PSD you can say, for position sensitive detector or position sensitive photo detector. Also, it is called as QPD and all. I'll come into that. So this is the scanner. This is a sample. So it can be scanned. So this is a piezoelectric material which actually controls the scanning of the cantilever, right? And there is a controller feedback loop. So whenever it changes its position, let's say to this number 1 point, so the voltage is somewhat different. So this difference in voltage, let's say delta V, actually creates some error, and this error is actually fed through this feedback loop, and that's why this now this cantilever changes its position. So this works in a feedback loop, right? So this is the basic ray diagram or basic schematic diagram of the atomic force microscope, right? So basically from this picture you can see it has mainly four component, that is probes or tips, you can say probes or tips, then cantilever for mounting the tips. These are basically, so this is a tip and there is some cantilever which is actually mounting this tip. So this is first part. There is a photo detector, right? There is a photo detector which is actually position sensitive with a laser source, because the laser source is actually like falling into this cantilever reflecting surface, and then we are getting the position of the reflection. The piezo, that is nothing but the piezoelectric scanner. This is a piezoelectric scanner, and then one feedback control module, right? These are the components of it. And there are some operational aspect I will also try to explain, that are alignment, then approach, then sample, stage, and raster, how these things are. So we will go one by one, right? So first, let us discuss the probe. So what are the features of the probe? So these are the typical probe that looks like this is very fine tip. So tips are most important components because that is actually going to measure the force. So that is actually going to respond in different force. Tips are the most important component of an AFM as it probes or scans the surface, right? So that this is the tip. Let's say this is the surface. This is actually scanning this. This is a tip. This is in some cantilever. This is the surface. This is cantilever, and this is my tip, and this is scanning. These are This is the closest approximation of a single molecule probing the surface. So this would be obviously very, very close so that it can feel the attraction. And we know, if we go by the like force with respect to the distance between tip and the probe, right? So at first, let's say this is one molecule is there, and the other atom is coming from the infinite. So whenever it is in the infinite position, that time there is no attraction, so it is in the zero. So the force, no attraction or repulsion, so the force is zero. So then after a certain time it starts in interacting. So it is actually it will attract. So it will like attract somehow. And normally in this plot we we show attraction as positive, sorry, attraction as negative force, and repulsion. This is the convention we are going to maintain. Repulsion as positive. So after a certain distance, it is going to attract. So then after so at some position, these two are come into contact. So that is the contact position. And then after that, if we try to like squeeze these two, it is going. So there is some electronic cloud in this number one atom, and these two also there is some electronic cloud. So these two are going to repel. So we are going to get some kind of repulsion force. So so that means, so up to this is attraction, and this after this point of contact, the repulsion actually begins. But the attraction is in this regime, up to this regime, the attraction is total attraction is actually higher than the repulsion, so that the whole region is actually attraction, and after this point actually repulsion becomes most prominent. And we know normally this attraction is in the order of r to the power 6, and this repulsion is in the order of r to the power 12. So these are very, very like weak force, and the works in very few, like if the distance is very, very high, that time these kind of forces are not going to operate. So there's a like question you can ask. So any two atoms or molecules are actually uh, interacting through gravitational force, but gravitational force is in the order of r, right? So when the distance is very, very less, that time these things are going to be prominent. When the distance is very, very big, that time gravitational interaction force is going to be prominent. So these are very, very small range, like the distance needs to be very less. That's what I want to say. Okay. Now, so this is the case. So this is overall attraction regime, and this is the repulsion regime overall. So let's just see. So this point, um, like more than this distance RC, let's say, there is no kind of attraction, repulsion, and everything, anything. So there is like these two particles are not interacting. Here also there is no interaction. But these two situations, let's say this is RT. These two situations are different. There no force is involving. They are in this position, the attraction and repulsion are same. That's why there is no net force. But here there is also no net force. But that is due to there is no force acting. And in this RT position, there is also no force, but that is due to attraction and repulsion are kind of uh, same. That's why there is no net force. So this is the force. This is the picture of dependency of forces dependency on the distance, right? So that means the tip is actually probing the surface in a very close approximation, and let's say we want to measure some atom in, let's say, some atom or some component which is having a, let's say, 10 micrometer diameter. So my tip needs to be very, very like less in the dimension than this probes, then the surface we are going to probe. So the tip size must be very, very like less. So if we can get into the, like, normally the tip size are in the nanometer, like 15 to 25, the diameters are 15 to 25, so that we can easily like probe the samples of and almost we can go to the atomic resolution now. So basically, the tip size and the tip geometry actually tells about the resolution. So depending upon the tip size, resolution of the AFM topography depends, right? Now this probe, this is the, let's say this is surface, and this probe comes, and this probe is going to measure the determine the force applied to the sample. And then depending upon the force, let's say the probe is going to the, like, attract, if it is in the attraction regime, the probe is deflect into this direction. If it is in the repulsion region, the probe will be going to deflect in the this region, and then we are, like, depending upon the force measuring, we are going to get the top. So that is a probe, that is the probe or the tip. Now the how this thing works, this is a surface, this is, let's say, my surface, and this is the tip and cantilever combo. This is a cantilever, and it is inside some kind of a piezoelectric scanner, and it is then this this is inside some, then this is in the whole instrument, like there's a position where the tip is actually mounted. So this is the cantilever, this is the tip, and this is the surface. Now the main that the AFM, so the AFM works in mainly three steps. At first, the tip senses the force across the sample, right? Then cantilever responds to this force by deforming. So let's say in this position, let's say this is the distance, right? So let's say this is the distance, this is r. Now whenever this tip is actually approaching, let's say there is in that this is the number one situation. Now this tip is in this position. Now the distance, let's say this is the r1 r. So r2 is less than r1. So that means, let's say if this is the force diagram, and let's say this is the RC, and at first this is, let's say, my R1 position. So at R1 position there will be no interaction, no attraction, and let's say this is my R2. So some kind of attraction begins at R2. So now this tip will be attracted. The tip will be at this tip will be attracted by this surface. So there will be some kind of attraction, right? And due to that, this cantilever will bend like this. So then if we like move into this direction with the distance, then it will like bend more and more. And we'll show this by picture. So this is the cantilever case. Now, after that, third step is it is to track the deflection of the cantilever. So then if we can track this deflection of the cantilever, because the cantilever is going to deflect according to the forces it senses, and the force is going to like implied depending upon the topography, depending upon the surface structure. So if we track the deflection of the cantilever somehow, then in terms we can know about how the surface looks like, how the topography of the surface is, right? So no problem with this. Now, how the cantilever can go, because we can easily see that there is a very big role of the cantilever, because it is going to deflect according to the force, and obviously these forces are not very big forces. These are uh, very small forces. So the cantilever should have the ability to sense the small force, so should have the ability of response in this small force regime. So one of the most important factors influencing the resolution which may be achieved with an AFM is the sharpness of the scanning tip, obviously tip. Then in order to measure small force 10 to the power minus 12 to 10 to the power minus 5 Newton, the spring constant should be as small as possible, because the force I am telling is nothing but the minus kx we already know, and this k is the spring constant. And what is the x? Let's say this is my equilibrium position, and from equilibrium position some kind of shift in any direction is happening. So this is the x. This distance, sorry, this is the x, and let's say up to this is r. So this is the deflection from the equilibrium distance is x. So that is what is nothing but the deformation or deflection of the cantilever. So that will obviously depend upon the force constant of the cantilever. So in order to measure small force, we are obviously going to have some kind of cantilever which constant must be small as possible, because that's why, and that's when it can sense the small changes in the force. A steep cantilever will not respond, because if the constant is that high, so these small forces cannot alter it cannot sense at all. So that is not going to fulfill my purpose. So obviously the cantilever should have some small spring constant, right? The cantilever resonance frequency should be higher than the instrument's data acquisition rate. Otherwise, we cannot And resonance, why this resonance frequency is needed, we'll tell about whenever we will discuss about the all the modes, right? All the modes. How what are the modes that can be used like that are used in the AFM topography measurements. The base tips may have a radius of curvature of only around 5 nanometer, and normally around this can be achieved using carbon nanomaterial, right? There are so this is the cantilevers. Cantilevers requirement is small spring constant, right? Now there are two mode of operation. From the force curve, you can easily see that as well. So this is my force versus distance. This is my force versus distance. So so this is the point of contact. Point of contact, right? So and the so this is the region from where this is the critical distance. After that, the attraction begins, and if R is greater than RC, there is no attraction. So in this regime, there is no point of contact, but still some kind of forces are actually some kind of force is actually occurring, right? So in if my tip and the surface distance is such that R is obviously less than RC, but greater than, let's say this is my RP, is greater than RP. So if it works in this region, so that there will be no contact. So that time if AFM measures, that is called non-contact mode. And after this point, like if this is in the RP or in the below RP point, that time it is called non-contact mode. And both the modes have some advantages and disadvantages. I'll try to tell that as well. Now there is also one thing that thicker and shorter cantilevers tend to be stiffer and have higher resonant frequency. Obviously, because if the cantilever is very thick, that time the deflection is going to be like any kind of deformation. That is, any kind of deflection is will be very difficult. Will be a bit difficult. So that times, so if we want to have some kind of want to measure some kind of very small force chain, we are going to have very fine and long uh, cantilevers, so that the changes in this cantilever, the deformation is very prominent. So uh, any thicker and shorter cantilevers will be stiffer, as well as the resonance frequency will be higher as well. Right. Now let's come to the, we already know this is the photodiode. So how this photodiode works? What is a photodiode? So photodiode is nothing but when light of a certain wavelength falls on it, a voltage is generated, right? Normally, photodiode can be think as a graph paper, right? Like in case of AFM, normally we have that quadrant photodiode because there is 4.1234, or it can be called as, because there are four different places. It is also called as split photodiode. But the most relevant name according to me is like position sensitive photodetector. So normally photodetector is whenever light falls, the voltage is generated. Right now, the what is position sensitive means? It means depending upon the position at which the light falls, the voltage that is generated changes or going to be different. Right, it's going to be different. Now let's say this is the enlarged picture of the photodiode. Although this photodiode is in the very like in some 200s or some in nanometer region, but just to show you, it is, let's say, the enlarged picture of the photodetector. So there is a position. Normally, this position is called as 0, 0. So whenever the light falls here, there is voltage generated is 0. Now, depending upon the position, let's say this position, it may be like 3 millivolt, let's say. Whenever you are going to this, let's say it is somehow like 5 millivolt or whatever in the positive direction. It can be again in these terms, it can be like minus 3 millivolt or minus 5 millivolt, like that. Depending upon the position, wherever the light falls, the voltage is going to be different. And so that if we measure the voltage, we can clearly say whenever, like, what is the position of the light falls, and that position of the light falls depends upon the bent of the cantilever. So in terms, we can tell about the topography, about the structure of that surface, right? So that is what laser beam. And normally how it is actually occurring, you can clearly see. So this is the cantilever, here is my tip, let's say, and there is the reflecting surface. So the laser source is coming like this, and change the color, and it is going like this, and there is kind of photodiode. So and this is the position. So whenever it got deflected into some direction, that time this is going to be somewhere here, let's say, and depending upon the position, we can tell what is the how much force is experiencing, and then how what is the, like, the structure, or what is the let's say the topography of the surface, right? There is no problem. And normally, that means the light is actually reflecting back to the detector. And that's why it is called, this process is called beam bouncing method. So the laser beam bounces off the back of the cantilever onto a position sensitive photodetector. As the cantilever bends, the position of the laser beam on the detector shifts. The PSPG itself can measure a displacement of light as small as 10 angstrom. So it can measure up 10, like, as small change as a 10 angstrom change can be measured. So an atomic resolution can be achieved, right? Right. If the tips are subness, and also all the things is that modulate the resolution, that determine the resolution, that keeps there fixed, then only we can measure up to like a very great resolution, right? So this is about the detector. Now let's talk about the alignment of the AFM. So this is, let's say, the cantilever, my cantilever, and this is the photodiode, and uh, this is the scanner. So this is the laser source, and there is the piezo scanner is there. So this, at first, what I know, this light needs to be fall upon this reflecting surface. This is the reflecting surface mentioned. So, and there is two screw. Let's say this is screw one and screw two. Let's say this works in X, this is works in Y. So just using this two screw, I need to take this cantilever into this. Sorry, I need to take this cantilever into this position. So it will come like this. Now let's say this will reflect towards some point. Let's say, now what we need? We need to take this photodiode into that position. So here, so this is reflecting in this direction. Now I need to take this photodiode to this position. Now here also two screw is there. Let's say again, this is my X, this is my Y. Like just the nomenclature I'm giving. Whatever it is, you can see whenever you are using the AFM. So depend, like, the moving this two screw, I can take this piezo diode to this position. Now the laser beam and the cantilever is all set, because the laser is coming and reflecting to and going to this zero position. Right, now the laser is set, but the surface is long, like surface is very far from the uh, cantilever or from the tip. So now after this alignment, this is the first step of alignment. So alignment is first. We need to like fall this laser light into the reflection plate of the cantilever. Then the photodiode needs to be aligned to the reflected beam position. Then after that, all this setup, this is the aligned setup. This whole setup needs to be moved towards the surface, and this is done by a stepper motor. Normal stepper motor normally does that. So how it is done? So let's say this is the positions. This is the one position, two position, three position, and four position. So at first we have given this. So what is the green point? I will tell. Just wait for some minute. So this is the, let's say, first position. There is no. This is in the no interaction region, right? Let's say this is the no interaction region. There is nothing. Now this tipper motor is actually working, and it is this tip is coming towards the surface. So after this point, some kind of attractive force started, or this is also in the, you can say, in the region like where there is no attraction. So if we think about if we draw like this, so this is the position one, let's say, this is position two, some kind of started. So this is also in the, so whenever the R is actually in this dimension, let's say less than 100 nanometer, then it is coming into this attraction kind of regime, right? Attraction kind of regime. So so now at this position three, let's say, let's just draw this again. So let's say this is my one. Sorry, this is the zero position. This is the zero position. So this, let's say, this is my first position. This is the second position, and here it is the third position. So at the third position, some kind of interaction is obviously there, and that interaction is attractive in nature, because the below part is attraction regimen and this part is repulsion regimen. And after this actually repulsion, this is repulsion starts. The overall is attraction, but the repulsion starts from this point, and this part is only attraction. So this interaction is only attractive. Now, after this point, let's say we are moving towards again moving towards the surface. So obviously at this point the interaction is starting. So let's say this is my position of the, at first this is the free position of the cantilever. Now as it is interacting towards surface. So the cantilever position is somewhat like this. It comes like this, right? And then whenever we are going and going, sometimes it is going to be in contact towards to the surface, right? But let's say the tip, let's say the tip is actually very stiff, it cannot sense that much force. So when the point of contact, let's say in that case, is for RK. So whenever the tip is very sensitive, the force constant is K is small, that time it will be very attracted. And when the the cantilever is very steep, that time it will not be attracted that much. So there will be no deflection. There will be that sense of attraction, feeling the attraction is very less. So if this is RK position and this is, let's say, RM, so that means RM position, RM position is actually great, because RM position we are measuring in terms of the folder, right? Because there is the motor, there is the motor. Motor is actually scanning this piezoelectric scanner. But this is the cantilever. Cantilever is actually feeling the force. The tip is actually feeling the force, so that cantilever bends. And in this case, the cantilever does not bend. So that means whenever the cantilever does not bend, the piezoelectric scanner or the motor needs to be work much more than this. So the distance of this motor or distance of this piezoelectric scanner, let's say, it will be higher whenever the attraction is going on. So that means there will be point of contact will reach earlier than the actual point of contact, and that is called jump to connect contact, jump to contact position. Normally this is the case, because there will be no such tip which will never attract or deflect. There will be some, but let's say this is the ideal situation when there will be no attraction, so that this there is a jump to contact, because before reaching to the ideal situation, the tip is actually connecting to the surface, and this is a jump to contact situation, right? So now you just try to see, if you try to see, let's say this is let's say my 1, 2, and 3, and then it is like, let's say, the uh, four position. Let's say this is the four position, this is my four position when it is actually jump to contact situation. Then after that, if we, then motor is still going. So after that, if we do not stop the motor, like there is jump to contact, now we are still moving this motor. So what will happen? let's say this, there will be the tip is now contact. Then after that, attraction is actually attraction limit is reached in this position. Let's say in the 5 position, attraction limit is reached. So then, if we like move this forwards, move this towards the surface, then it will going to reach. So this 5 position is the point of contact. Let's say. So then after that, it is going to reach in the repulsion regimen, right? So now tip is in contact. Tip is in contact. It cannot do anything. But now the cantilever is going to be repelled by this repulsive force. So this bend will be like this repulsive force will be in this direction, repulsive force. So the bend is going to be straightened. So there will be a point that, let's say this is the point 7. So there will be a point when there will be the repulsive force and attractive force is going to be similar. So that time there will be again no deflection. So this point 5, so the point 1 and point 7, the bending of the cantilever is same, but here no attraction or repulsion is actually there with the surface, but here the amount of attraction force and the repulsion force is similar. So that's why there is no deflection. Then let's say this is the 7th position, then still the motor is not like switched off. So then what will happen? Now the surface is actually there, but due to the repulsion, then what it will do? Like from this, let's say this is the upward curvature. So then after the repulsion is will be higher. So in this regime, the repulsion is much higher. So just only repulsion is working on. So the steep is going to be like the curvature is going to be downward. So from this position, from this from this upward curvature in the point of contact, then the repulsion begins and the actually curvature so it changes like this. So you can, if we see like this, let's say this is the photo detector position. Now at first, it was in, then whenever there is no deflection, so we aligned it like this. There is no deflection, it is coming to the 0 0, let's say. So zero, not 0 0, like a 0 voltage position. Now, so the whenever the attraction is there, that time it is, let's say, moving towards this, like 2 3 4 5. After 5, this is the most negative voltage position because this is the highest attraction. After that, whenever we decrease the distance, that time it will again move toward, because this is going to be positive voltage, move towards this direction, and this will be again, this will be the 7th position and this is the 5th position. Then after that, we are going to get some positive. Let's say this is the 9th position. After that, this is in the only in the repulsion regimen, and this is only in the attraction regimen. So, and this is my 1 and 7. There is no interaction, and that is the equal amount of attraction and repulsion. So that is going to be the case. So now, if we like increase the decrease the distance more and more, so after certain times, so let's say this is the Peugeot scanner. So after certain time, whenever we whenever we decrease, let's say this R is very less than like let's say this is let's say RT. So very less than RT. So it is in the high repulsive regimen. So it will eventually broke down, right? So we need to set some point so that, and also one needs to remember that imaging, AFM imaging is only done in contact mode, obviously, is only done in in positive voltage, or not positive voltage, let's say in repulsive force, right? Obviously, it is in the contact mode because it is already in the point of it is already in the contact now. So this is the contact mode. So normally imaging is done in contact mode and in the repulsive force regime, right? So this is the case. But you can clearly see. So this is the first position, then it is approaching towards. So this cartoon can clearly explain the things very easily. So then it is happening like it is approaching towards this. So after that, some kind of curvature you can see. This is the kind of curvature, and then after that, whenever it is going in the repulsive region, the curvature is changes. It is like this upward. This is like downwards, right? And this green point is the set point or the set voltage. So you said this is my set. Whenever, let's say you said the plus 4 millivolt is the set point. So whenever it is in the plus 4, you are telling this is the set. Now it is, let's say this is your surface. So at this point it is in the plus 4 millivolt, right? Let's say for position. Now whenever this distance increases, so that means the repulsion is going to increase. So it is going to be in much more like the position will be in the much more positive. So let's say it is in the 6 millivolt position. So there will be a error in the voltage, error in voltage from set point, right? So you said this is my position. This is a plus 4 position is there. Whenever the due to the surface topography, it is going to change. So this error, this much error, let's observe that is going to be feed through the feedback loop, and then the piezo scanner will move like, right. So let's say this is the distance, so then it will move upwards and maintain the force. Again here it will be, let's say, plus 2. So then again it will come to the feedback loop and again it change the side. So at first it will go by the constant height, and then depending upon the force, depending upon the error voltage, it will changes the height of the piezoelectric scanner. So now let's say this is your surface, and then your piezo scanner position will be like this, then this, this, this. So if we just get the piezo scanner's position, so we can get the idea of the how the surface looks like, right? No problem in that. Okay, so this is the basic idea of alignment. And what is raster scanning? Normally, raster scanning is nothing but point by point scanning, right? This is point by point scanning. This is called raster scanning, and that is controlled by also the piezo. So at first, let's say it starts from there, this point. So starts from this point, and it moves towards this, then come back to this and this. So this is the scanning mode, and that is so that is what we already said. So this is the contact mode. At first it goes to the some height defined about by the set point, and then it go like this, and depending upon the position of the video scanner we can get this, and this is the contact mode. Uh, So this is the picture of constant. A constant mode, a contact mode can be in the constant force, where we are changing the force according to the like maintaining the force and the changing the height. And one thing can be constant height when there is no change. So just the by the height we can directly get the image. So you can see in the constant force at first this is coming like this only, and depending upon the feedback it is changing its position to this. So constant force is nothing but first step is constant height, then second step is constant force, and that means constant height is just the first step. So this is the contact mode, and it has some advantages. Let's just allow them to. So I was talking about AFM. Some this is the contact mode. Normally imaging has been done in contact mode. So what is the advantages of contact mode? This is high scan speed. Atomic resolution can be obtained on a hard surface, can image fairly rough samples, but this has some disadvantages because it is in the contact mode towards the surface. So the chances of damaging surface damage, and also the tip damage. This is the biggest problem in contact mode, right? Also, just due to the contact. There can be capillary formation by the ambient water molecule as also, and mainly the sample damage is also one of the things. So that is a disadvantage. So now there is also the non-contact mode. So just by the going towards the force, okay, just tell me one thing. Let me tell. So in this class, I'll just discuss. At first, I will discuss about like, so in this class, I'm discussing about the AFM. Then I will solve the questions of the assignment 8, right? And then after that, uh, I will just give a discussion about the revision, right? Because yes, tomorrow is your class, so I'll also give a brief revision. So what are the things? Not as such, like teaching anything, just the things that are being covered. So what are the things you need to read before going to the uh, class? So this is the non-contact mode is. This is the point of contact. So in this regime, something is working that is in the non-contact mode. So in this process, what happens normally? This is the tip, this is the surface. Let me allow him. Now in non-contact mode, this tip normally vibrates. It vibrates, right? Let me just take the highlighter so that you will understand. Okay, yeah. So it vibrates in this way, right? And depending upon the vibration, so whenever, let's say, whenever it is like this is, let's say this is the topography of the surface. So whenever it is in this direction, so the vibration will be affected because the distance between this tip and surface is somewhat different than whenever the tip is here, right? So the change in the vibration frequency, because the tip is always vibrating in a definite frequency. This is the resonant frequency of the tip. And then depending upon the surface, as this like the force is actually going to interact with that, so the vibration will be damped or over damped or whatever it is. So then depending upon the distance between, so depending on the topography, this vibration is going to change, and that's how we are going to get a, like, changing in the vibration resonance or the vibration amplitude of the vibration, we are going to get the picture. Yes, but so that is similar kind of non-contact. But in case of non-contact mode, similar kind of contact. So in case of contact mode, the tip is directly in contact with the surface. This is the tip, and that time it is actually measuring the changes in the forces. And here it is just an indirect method, indirect process of measuring the vibrational amplitude or the frequency changes depending upon the force. So these two are same, but as there is very like there is a big gap between this tip and the surface, so the resolution in case of non-contact mode is very weak, and normally imaging is not never done in this non-contact mode. Normally in case of the, you have already learned in the classes, the magnetic force measurement or the electric force measurements has been done in non-contact mode. So what is non-contact mode? It is nothing but the surface, the tip is actually maintaining some distance from the surface, and it is actually vibrating with some frequency always. And depending upon the topography, this vibration frequency or the amplitude of this vibration is going to change. And from that change, we are going to measure the topography of the surface. And this is normally never used in imaging, but this is a very new thing. This is actually using in case of any polymer or soft surface or the DNA biological surface, that is intermittent contact. So what happens? So this is in between the contact and non-contact mode, and it uses both the advantages of the contact and non-contact mode. So in this case also, the tip is actually vibrating with with this resonance frequency, but it is not that much far, that so that it never touches. But it is like, let's say this is the position, and due to the vibration, let's say it is coming sometimes. Sorry, take the color. So due to vibration, it is vibrating like this now. So sometime it is touching this, and the other position is like this. So it is always vibrating or oscillating, you can say, oscillating in this frequency. So sometimes it touches, but it does not touches for longer. So as it touches, right? So obviously there will be some kind of change in the frequency or some kind of change in the amplitude. But as it touches sometime, so the resolution will be much higher. So in case of non-contact mode, there is never that the tip is never touching the sample. So that's why the resolution is less. But in case of this intermittent contact, there is contact, but the contact is not that much longer, so that it can damage to the surface or tip can be damaged. But the contact is enough so that the resolution gets better, right? So this is nothing but the intermittent contact, and that is the that is normally is in the regime of like this. So this is the intermittent contact. So in this regime, right, it is already mentioned here. So just touching the surface and coming back, right? So it is like this, touching the surface and coming back. So now let's say this is the surface. So whenever, let's say this is my free movement, let's say up to this, right? This is the free movement of free vibration. So the distance is like from, if it is the equilibrium position, so in this direction up to this it is going, up to this is going, let's say. So whenever it is in this position, so the tip can, let's say tip should go up to this position, but as the surface is there, it cannot go. Let's say it is going only this up to this. So this is, let's say, delta x1, and this is delta x2, can, because it cannot go further, and delta x2 is lesser than delta x1. And in case of this, tip should go like tip is going like the total. So that's why the difference in this movement of the vibration actually going to determine the structure, determine the topography, determine the structure, yeah, determine the image of the structure of the surface, right? So that is the intermittent. And so this is the case. Let's say this is the free fall up to this. This is the deflection range. But whenever it is near about the surface, that time it cannot go. It should go like up to this, but it is only going up to this, right? I think you understood. So let's say in case of free vibration, we are getting this position. Like in case of contact mode, we are only getting the 0 point. Now, as it is vibrating, so we are always getting, like, let's say this is the free resonant position. So whenever it is kind of in the surface, so instead of this point, let's say this is the point it should go, but instead of this, we are getting only up to this. And whenever it is like much more, let's say, so the point will be much more lesser. So and like that, this is one, this is two, let's say this is one, this is two. So depending upon that, we are going to get the picture, right? So let's just go solve the questions, then we will finish this discussion, and then we will go for the revision class, right? So which among the following statement is correct? Non-contact mode is good for to measuring long-range attractive force. So non-contact regime is this regime where there is only attraction, and that is long-range attraction force. So that is true. Intermittent contact mode in FM is best for measuring mechanical properties. So intermittent force is like sometime it is touching the surface and sometimes it is not. So at the same time, it is giving the best resolution as well as the other properties. So it is actually used in case of uh, like, sorry, it is kind of like used in case of measuring the mechanical properties. Okay, and in case of contact mode, the friction or adhesion force. That's what that mainly in case of contact modes we are actually dealing with the uh, repulsion, right? Because this is the point of contact, and before like after that, whenever we are going, it is only the repulsion regime. So this is the repulsion kind of force, that is friction or adhesion. We are going to measure in contact mode. So non-contact mode and intermediate is right, and contact mode is also obviously measure friction adhesion. So all of the above options are right. So the second question: the resonating frequency of a thicker or shorter cantilever is relatively higher same as the normal ones, relatively lower, depend on the ambient condition. So I already discussed whenever I was discussing the cantilever, right? So a thicker and shorter cantilevers tend to be stiffer and have higher resonant frequency, right? So, so the what is cantilever is doing practically. So this is the cantilever. So depending upon the force, the tip senses cantilever is actually bending upwards or downwards. So that means the cantilever, whenever the force constant of the cantilever is small, that time it can respond towards this small range of force. Whenever it is high, that time it cannot. So now, if the cantilever is very, very thick or very short, that time obviously with a very thick one, that time it cannot sense the force, and also the frequency is going to be higher. Right? I already discussed this. Yeah. Now also I discussed. So this is the answer. Now, which of the following parameter determine the resolution of an AFM image? So, AFM, the parts are tip and cantilever, first one. Second one is laser and the photosensitive, position sensitive photodetector, right? Thin number is like the piezoelectric scanner, right? These are the things. I already, here you can see that what are the components. So probes or tips and cantilever for monitoring the tips, photo detector with laser, the piezoelectric scanner, and the feedback control module. Right. So these are the main part of the AFM. Now, obviously, you can you know that the tip size, right? The size of the tip. If the size of the tip is very very big, so the resolution is going to be less because it cannot it cannot separate differentiate between small particles and the small particles. So the resolution is obviously going to be depend upon tip size. If it is circle, so then also the all the part is going to interact, so the resolution is going to be less. So we need an atomically sharp so that we can achieve atomic resolution. So very sharp. So the tip size and geometry obviously. Now I already told you that in case of contact mode, mainly there are three kind of mode: contact, non-contact, and intermittent contact mode. So in case of contact mode, it is actually touching the surface, so that there is a problem of like deforming the substrate, deforming the T. So that's why the resolution is not great, right? And I'll show in the third or fourth question that there I have put a picture of contact mode and intermittent contact, how the resolution changes. So obviously contact mode and non-contact mode normally cannot give a good picture because it is in the very far from the surface, right? Very far from the surface. So the image quality will be very 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 bad. So never, like, people don't use even non-contact mode to get an image. Always normally use the image mode is in the contact or the intermittent, normally in the intermittent, but contact can also, but it has some problem of deformations. So obviously mode of scanning is going to determine the resolution. And spin constant of the cantilever, that is very very important, because what we are measuring nothing but the deflection of the light, right? This is the position of the photodetector and there is the reflecting surface. So laser is coming and it is going to this position. So whenever the force is there, very attraction force or reflection force, depending upon that, the cantilever is actually bending. Cantilever is actually bending. So so let's say this is like this now. So as it is bent, so that time the position is going to be changed, and we are going to get the position. So now, if the spin constant of this, what is spin constant? That if F is minus kx, k is the spin constant, x is the deflection. So if the spin constant is very very high, if the spin constant is very very high, it will be very difficult to be deflected. So that and the forces acting that are very very small. So obviously we need to have some cantilever which is going to have less spin constant, so that it can sense the small changes of the protrusion on the surfaces, small changes of the topography of the surface, right? So obviously spin constant of the cantilever is going to have some role. So that means all of the above answers are right. The alignment step is done in AFM. I already said about the alignment. Okay, again coming back to going back to the alignment step. What is the alignment? Yeah. So at first there is the cantilever, right? This is the cantilever, and this is a laser source. So cantilever needs to be aligned such that the laser falls onto this reflecting part, and like this. So this is the first step of the alignment, and then this photodiode needs to be aligned such that the reflected light, this reflected light, this should be the position of the photodiode, right? So this is the first step. So this is the alignment, right? So what is the question now? You know the alignment. I told you about the alignment. Now the alignment step is done in AFM so that the laser falls on the reflecting part of the cantilever. Obviously, that is the case. So it should the alignment step is mainly the reflecting part of the cantilever. So this is the reflecting. This is the
Sir, your screen is not visible.
screen is not visible.
Yes,
Yes,
sir.
sir.
Okay, let me check it. Oh, sorry, somehow it got disconnected. Is it visible now?
Yes,
Yes,
sir.
sir.
Now
Now
it is
it is
visible.
visible.
Oh, okay. Sorry. Yeah. So what I was telling, so that this is the cantilever and this is the reflecting surface. So at first, this so laser is fixed. Laser is coming like this. Let's say this position. So there is the piezoelectric scanner. So I need to move this cantilever such a position so that the laser reflects on this, right? So now let's say this is the position. This is the so this is the now the position of the cantilever. So I need to do this from this. Well, this is the first position, let's say, and this is the second position. So this is the alignment. So laser falls on the reflecting part of the cantilever. So that is the first step of the alignment. Then the photo detector needs to be aligned such that it comes into this way. So this is the reflecting light. So now photo detector needs to become like this position. So this is the second step of the alignment. The alignment step is done in AFM so that the laser falls on the reflecting part of the cantilever. Then laser reflects and falls at the origin of the QPD approach of the. So that this is also the step of alignment, but this is the first step. That's why maybe this is the first step alignment of the alignment step. Normally, the approach is then after this all these things, like this is in the condition. Let's say this is the cantilever tip, and this is the position of the QPD director, and then let's say this is the surface. So now it comes down, and that is called the approach, and this is called the alignment. So alignment is nothing but the laser falls on the reflecting part of the cantilever. So this is the answer. Which mode of an AFM is best for scanning a chemically patterned surface? Right? So with uh, non-contact mode is not great, and also contact mode is actually going to, if the surface is so good, like the pattern is very great, so in contact mode it can be like distorted, it can be deformed, right? But like whenever you are in the intermittent contact mode, that time, like the imaging, overall imaging is great. But if we want to get the great details of the surface, then obviously as the contact mode is like always contacting the surface. This is the surface, and this is the tip. It is in the contact mode, and in intermittent contact, it is sometime it is there, sometime it is there. So overall picture quality is great in this, and there is no chance of degradation of the sample or breaking of the tip. But if you want to get a greater details of the so that's why it is written the chemically pattern. So the surface is actually very having some kind of reconstruction, some kind of very fine pattern. So that time, obviously, the resolution is going to be higher in case of contact mode because it is in the it is in the like direct contact with the surface, right? But in case of a soft material, where the problem is with the sample damage, obviously we are going to have the intermittent contact. But if it, normally red patterns can be fine from the contact mode, right? So there is no problem. Already I talked about the tapping mode. So this is the mainly this is the resonance, and these are the frequency. Let's say uh, like vibration frequency. Like after these two are actually from this position. Let's say this position one and this position one. So these are depicting in this picture. This is the intermediate. So obviously, whenever we are going to get a great pattern or the finer details of the surface, we need to have the contact mode. But whenever there is a problem of the surface sample damage or the thing, overall get resolution can be achieved from intermittent contact. So that's why I told solving while solving the previous question. So this is the contact mode and this is the tapping mode. So and that is a DNA. DNA is a soft material and it normally got damaged in this contact mode. But in case of tapping mode, we are getting the great details of the structures, right? So now come back to question 6. The XY motion of the tip is controlled by the, we know already that is a piezoelectric scanner. So piezoelectric scanner is like, this is a piezoelectric scanner, this is the cantilever, and this is the T that is there. And piezoelectric scanner is, what is piezoelectric material? Depending upon the voltage, it changes its dimension. So depending upon the force, we are getting some different kind of voltage in the QPD of the detector, and that voltage is actually coming in the feedback loop and providing this piezo scanner so that it is changing its height, like changing its height or changing its position. So this position XY position is actually maintained by the piezoelectric scanner. Which of the following is a disadvantage in contact mode scanning? High possibility of tip damage. Obviously, we know already. I already discussed this because other things is okay. It can be done for rough samples. Normally, rough samples are done in contact mode only. Very poor resolution is not the case because the resolution is great and slow scan speed is also not the case. So the case is the damage because it is in the contact mode. So that there is a there is a possibility of the tip damage. Also the surface damage. The purpose of feedback loop in AFM is, so what I said, the purpose is to, so this is the cantilever again. I'm many times I'm like drawing this picture. This is the surface. Let's say this is the surface. So whenever it is here in this position, let's say, so that time it will be in the like, let's say this is the first position and let's say this is the second position. So in this position the attraction is going to be, because it is not in the contact mode. So this is in the, now it is attraction is going to be higher. So so the, so now we so what is happening, like in, let's say this is the constant force I am talking about. Let's say this is the F. Now as this attraction is higher, so there will be some F1 changes of the force, and that's why to maintain the force again, obviously this piezo scanner will try to push this towards the same position than like the previous one. So this thing, this change in this position due to the maintaining the constant force is done by the feedback loop. So how it is actually done? This is the position. Let's say this is my set point. So at first here it is actually falling. Now due to the topography, it changes towards, let's say, this position. So at first, this is my first position. So this is my second position. So there is a change in the voltage because this diode is position sensitive. So there is a change in the voltage. So now this voltage is actually going to the feedback loop and tells the piezo to change the position. That means change the position of the what? Cantilever. So the purpose of feedback loop is FM is align the tip with the substrate, align the cantilever deflection, align the laser source with QPD. None, because laser source is done by the screw in the laser part, right? Screw in the detector part. So that means as the piezo part is in the cantilever section, so it is it is due to the alignment of the cantilever. That is the answer, right? What is the typical diameter of the FMT? So normally it is in the nanometer range, right? Angstrom range is not possible to achieve, and so the best resolution, like it should be typically speaking, it should be as low as possible. But after that, it is not possible. Like after 10 to 15 nanometers, it's not possible. Normally this, but using the carbon nanorod and CO also, one can reach up to like 2 nanometer or 5 nanometer. That is there, but the typical diameter is in the 15 to 25, not the millimeter. Sorry, sorry, my mistake. It is in the nanometer. Yeah. Which type of material the AFM scanner is made of for correction of error generated due to the topography of the sample? So I already said. So the this is the photodetector. Some error is generated depending due to the topography. Some error is generated. So this is the error in voltage. Let's see, error is generated, and this is going towards feedback, and then the piezo scanner is changing. So this, which type of material the AFM scanner is made for the correction of the error. So the correction of error is done by the piezo material, right? So these are the questions. Okay. So these are the questions for today's class. Now, I will like yesterday is your sorry, not yesterday. Tomorrow is your exam, right? I think so. I will try to tell, like, not discuss anything. You can ask me if something comes. I will try to explain. Or like I also don't remember all the things at a glance, but still I'll try to solve your questions. If you can ask, if you can ask anything, just I will tell something like what are the things have been taught already, and what are the main important things that can be found in either my class or in the search class that should needs to be taken care of before going to the exam, right? So